Okay, let's take a look at some motion. So a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, about 109 miles per hour. There's a figure. Oh, I'll just draw that. And then it reaches a height of s, that's like a position function. Oh my goodness, it's like it makes sense with what. All right. And that's 160t minus 16t squared feet after t seconds. How high did the rock go? All right. So first of all, let me show you that picture. So let's think of that. So there's some explosion, and the rock shoots upwards. The position when right before the dynamite blew up, the position was 0. So we're considering the ground to be 0, and then it goes up some distance s. Or some position s. So there we go. And question A, or part A, says, how high does the rock go? How can we figure that out? Well, we could just plug in a bunch of values and see which one's the highest one. But really, we could do something more fancy than that. I know that if I take the derivative of the position function, I get velocity. So that's like, why would you need that? Well, I also know that at the very peak of this, the rock's, path, at the very peak, the velocity is 0, because it has to stop and turn around and go the other direction. I mean, it doesn't have to turn around, but it has to stop and then go the other direction. To change direction, to go the opposite direction, you have to stop at some point. So, if I take the derivative here, which is what I'll do. So I'm answering, how high does the rock go? Well, I'm going to take the derivative. So v of t, that's going to be the derivative of this. So d dt. I'm taking the derivative of all this stuff. That looks ugly, so I'm not going to write that. So I take the derivative, and I just get 160, and then what is this? Minus 32t. I take this down, multiply it, and then subtract 1 from the exponent. So here it says, okay, we have the velocity function, and I know at the peak of its trajectory, the velocity equals 0. So I can set this equal to 0. And that's 160 minus 32t. And solve, this would be 32. I just add 32t to both sides, and I get 160. And I'll divide by 32. Okay, that's very nice. It's 32. Okay, t equals 5. So this is not how high it goes. This is the time at which it reaches its highest point. Right? Because I start off and I'm shooting up, and then I get a velocity of 0. Oh, text mail. And then, so it shoots up, and then at 5 seconds, at 5 seconds, we've reached our maximum height. So how do we find that height? Well, you take the 5 and you plug it in for the t value there. So this is our answer to A. And I'm just going to do that in my calculator. So if I plug in that 5 to this and this, I get 400, I think. 400. And that's measured in feet. So that's 400 feet. Beautiful. Beautiful. How did I know that? Let's review real quick. At the height, at the very peak, I know that the velocity is 0. So I took the derivative of position to get velocity, and then set velocity equal to 0. Found the time. So at time t equals 5, I knew that I had a velocity of 0, which meant it was at the peak of its trajectory. And then I plugged that into the position function. Okay, let's see. What is the velocity and speed of the rock? Ooh, velocity and speed when it is 25 feet from above the ground on the way up and on the way down. It actually should be the same speed, right, for both of them? But one will get negative for velocity, one will get positive for velocity. That's crazy. So, what is the speed? No, sorry, what is the velocity and speed of the rock when it is 256 feet above the ground? Okay, this is interesting. Some people might think, oh, you just plug in 256 to the velocity function. Wrong. 256 is feet. T is in seconds, so I can't do that. The only function that I have that deals with feet is the position function. So I have to set the position function equal to 256 and then solve. So that's what I'll do. So what does this mean? This is saying, well, if I were to solve this, it would give me the t values, because there's two, t values when the rock is 256 feet above the ground. And there's two t values when it's above the ground, 256 feet above the ground. On its way up, it reaches 256, maybe goes a little more, and then it's on its way down. It hits 256 again and then keeps going. So that's why there are two answers here, and we can just set it up like a regular quadratic and solve. So let's do that. And minus 1, I'm getting everything to one side. Plus 256 equals to 0. I can factor out a 16 first. So I get t squared minus 10t plus 16 equals 0. In a factor, I could divide by 16 and it goes away, right? So I'll just ignore it. Hopefully you understand that. And then we have, what, 16 in the top, negative 10 in the bottom. 8 times 2, negative 8 and negative 2. So we have t minus 8 and t minus 2 equals 0. Come on! Alright. So actually I get t equals 8 and t equals 2. This corresponds to the way up, I would assume, and this corresponds to the way down. So, but that wasn't the question. The question was, what is the velocity and speed of the rock when it is 256 feet above the ground and on the way up and on the way down? Okay, so I have to take these t values and plug it into my velocity function. So when I plug in t equals 2, so for t equals 2, what happens? And I'm just plugging it in there, it gets 96. And the units would be, well, this was in feet, and then this would be feet per second. So this would be feet per second, because t is in seconds. And then v of 8, so these are the velocities. If I plug that in, I would get negative 96 feet per second. So that makes sense. So those are the velocities. The speed, remember, is just the absolute value of the velocity. So the absolute value of the velocity equals the speed. So that's just 96 feet per second. And it's the same on the way up and on the way down. Cool. So that's the answer to part B. I'm running out of room. Part C, what is the acceleration of the rocket at any time t during its flight after the blast? What would this mean? What would this mean? What would this be? Well, hopefully you know. All we have to do is take the derivative of the velocity function. So this, take the derivative, d dt, and I would get the acceleration function. Ho ho ho. And then that would just be negative 32, no matter what. But we got to think of what are the units. And for acceleration, that's just feet per second squared. Yeah, feet per second, or feet per second squared. All right, that's pretty nice. What is this last thing say? When does the rock hit the ground? Well, how could you figure that out? Actually, this is C. I'll label that. And then part D. When does the rock hit the ground? Well, it hits the ground when S equals 0. And it happens at 2 times. When t equals 0, and then when t equals something else. So I'll just set the position function equal to 0. So 0 equals 160t minus 160 squared. Okay. Well, I can just factor out a 16t, right? Yeah. This would be 10 minus t, so equals 0. So one of the times is t equals 0, because if I set that equal to 0, then I get t equals 0. All right, we already knew that. And then the other time is at 10 seconds, it looks like, right? Because I could say 10 minus t equals 0, add the t over, and I get t equals 10 seconds. So these are both in seconds. So does that answer the question? When does the rock hit the ground? Hit the ground, so that would be at t equals 10 seconds. All right, that was a long one. Goodbye.